Welcome back to our AI series. In episode 10, we'll delve into the fascinating world of computer vision. We will cover the basics of computer vision, image processing techniques, convolutional neural networks, CNNs, a hands-on image classification project, and advanced topics like object detection and segmentation. Let's dive in. 1. Basics of computer vision. Computer vision is a field of artificial intelligence that enables machines to interpret and make decisions based on visual data. It's about teaching computers to understand the content of images and videos just like humans do. This includes recognizing objects, understanding scenes, and detecting specific activities. Computer vision is utilized in various applications, from self-driving cars and facial recognition systems to medical image analysis and augmented reality. The primary goal is to automate tasks that the human visual system can do. 2. Image processing techniques. Image processing involves various techniques to enhance, analyze, and manipulate images to achieve desired outcomes. Here are some fundamental image processing techniques. 2.1 Image enhancement. Image enhancement involves improving the visual appearance of an image or making it more suitable for analysis. Techniques include 1. Histogram equalization. Adjusts the contrast of an image by distributing the intensity values. 2. Filtering. Removes noise or sharpens details using filters like Gaussian blur or edge detection. 3. Morphological operations. Enhances the structure of objects in an image, using operations like dilation, erosion, opening, and closing. 2.2 Image segmentation. Image segmentation is the process of dividing an image into multiple segments to simplify or change its representation, making it easier to analyze. Techniques include 1. Thresholding. Separates objects from the background by converting grayscale images to binary images. 2. Edge detection. Identifies the boundaries within images using algorithms like Canny, Sobel, or Laplacian. 3. Region-based segmentation. Divides images based on regions with similar properties, such as color or texture. 2.3 Feature extraction. Feature extraction involves identifying key features or patterns within an image to represent it in a more informative way. Techniques include 1. Scale invariant feature transform, SIFT, detects and describes local features in images. 2. Histogram of oriented gradients, HOG, describes the distribution of gradient orientations in an image. 3. Speeded up robust features, SURF, detects and describes features quickly and robustly. 3. Introduction to convolutional neural networks, CNNs. Convolutional neural networks, CNNs, are a type of deep learning model specifically designed for processing structured grid data like images. They have revolutionized computer vision by providing exceptional performance in tasks such as image classification, object detection, and segmentation. 3.1 Structure of CNNs. A typical CNN consists of several layers, including 1. Convolutional layers. Apply convolution operations to the input image to extract features using filters. 2. Pooling layers. Reduce the spatial dimensions of the feature maps, typically using max pooling or average pooling. 3. Fully connected layers. Flatten the feature maps and connect every neuron from one layer to the next, similar to traditional neural networks. 3.2 Activation functions. Activation functions introduce non-linearity to the network, enabling it to learn complex patterns. Common activation functions in CNNs include 1. ReLU, rectified linear unit. Replaces negative values with 0, keeping positive values unchanged. 2. Sigmoid. Maps values to a range between 0 and 1. 3. 10H. Maps values to a range between 1 and 1. 3.3 Training CNNs. Training a CNN involves optimizing the model's parameters to minimize the error in its predictions. This is typically done using 1. Backpropagation. Computes the gradient of the loss function with respect to each weight by the chain rule. 2. Gradient descent. Adjusts the weights to minimize the loss, using techniques like stochastic gradient descent, SGD, ATOM, or RMS-prop. 4. Hands-on. Image classification project. Let's dive into a hands-on project to build an image classification model using CNNs. We'll use TensorFlow and Keras for this project. Step 1. Install necessary libraries. First, we need to install the required libraries. Explanation. These commands will install TensorFlow, NumPy, Matplotlib, and Pandas libraries which are essential for building and training our CNN model. Step 2. Import libraries and load data. Now, let's import the necessary libraries and load the CIFAR10 dataset. Explanation. Here, we import TensorFlow and Keras modules, along with Matplotlib for visualization. We then load the CIFAR10 dataset, which consists of 60,032 by 32 color images in 10 classes. We normalize the pixel values to be between 0 and 1 for better training performance. Step 3. Explore the data. Let's visualize some of the images in our training dataset. Explanation. This code snippet displays the first 25 images from the training set along with their class names. It helps us understand the type of images we are dealing with. Step 4. Build the CNN model. Next, we'll build our CNN model. Explanation. In this code, we create a CNN model using Keras sequential API. The model consists of 3 convolutional layers followed by max pooling layers to reduce spatial dimensions. After the convolutional layers, we flatten the output and add 2 fully connected, dense, layers. The final dense layer has 10 neurons corresponding to the 10 classes in CIFAR10. Step 5. Compile and train the model. Let's compile the model and start training. Explanation. We compile the model using the Atom Optimizer and sparse categorical cross-entropy loss function, which is suitable for classification tasks. We then train the model for 10 epochs, using the training images and labels, and validate it on the test set. Step 6. Evaluate the model. Finally, we'll evaluate our model's performance and visualize the training results. Explanation. This code snippet plots the training and validation accuracy over the epochs, helping us visualize the model's learning progress. We then evaluate the model on the test set to get the final accuracy score. 5. Object detection and segmentation. Object detection and segmentation are advanced computer vision techniques that go beyond simple image classification. These techniques involve identifying and localizing objects within images and delineating them from the background. 5.1 Object detection. Object detection involves identifying the presence and location of objects in an image. Popular models for object detection include 1. YOLO, You Only Look Once, real-time object detection system that divides images into a grid and predicts bounding boxes and probabilities. 2. SSD, Single-Shot Multibox Detector, detects objects in images using a single deep neural network. 3. Faster RCNN, combines region proposal networks with convolutional networks to detect objects in images. 5.2 Image segmentation. Image segmentation involves dividing an image into segments to identify objects and boundaries more precisely. Techniques include 1. Semantic segmentation. Classifies each pixel of an image into a category, such as car, road, or tree. 2. Instance segmentation. Identifies and delineates each object instance separately, such as detecting each individual car in an image. 3. Panoptic segmentation. Combines semantic and instance segmentation to provide a complete understanding of the scene. Conclusion. In this episode, we've explored the exciting field of computer vision, covering the basics, image processing techniques, convolutional neural networks, a hands-on image classification project, and advanced topics like object detection and segmentation. Computer vision is a rapidly evolving field with numerous applications that impact our daily lives. Don't forget to like, subscribe, and turn on notifications to stay updated with our latest content. If you have any questions or topics you'd like us to cover, leave them in the comments below. See you in the next episode.